All right, this is the 2010 AMC 10B problem number 16. A square of side length 1 and a circle of radius root 3 over 3 share the same center. What is the area inside the circle but outside the square? Well, let's draw real quick. We'll make a square. I'm trying to make a little bit bigger drawings, as some of you have mentioned that the drawings are kind of hard to see. The problem is when I draw bigger, I don't always draw as accurate as I do when it's a smaller diagram. So I guess that's not too bad this time. Okay, so there must be a part outside. How do we know? Because if there wasn't any part outside the square, the answer would have to be 0, and none of those are 0. So we can just use that reasoning. So the center would be here, and we have a radius of root 3 over 3. How are we going to get that, right? Well, if we think about it, usually you want to connect a center with a radius, right? You want to draw a radius somewhere, or if there's two circles, connect the centers of the circles, but we only have one circle. So if you're going to draw a radius, don't draw it to some random spot, right? Draw it to a spot that might help. And if I connect it to where something is happening, namely the intersection of the square and the circle, you're going to get this sector that looks like this. Okay, so now we have a sector. If we knew the central angle, maybe we could do the sector minus the triangle and then multiply that by 4, because they're all going to have that same situation, whatever that is. Okay, so how can we do that? What else do we know? Well, we know this is root 3 over 3. Let's make that triangle a little bit bigger, actually. So we'll go like this. So this is root 3 over 3. And we know that from here down to the side, right here, we can make a right triangle if we do that. And this height right here is going to be half of the side length, because it's the center of the square also. So this going down is actually a length of 1/2. Okay, then let's call this x, and let's just do Pythagorean and see what happens. You're kind of looking for more information. You don't really know what to do just yet. And it's not really obvious with these two values. Maybe if we add this one, we'll see something that might help us progress in the problem. So a half squared is 1/4 plus x squared. Root 3 over 3 squared is 1/3, because it's 3/9, 1/3. Okay, then this is actually 4/12, and if I minus 3/12, I will get 1/12, and if I square root, I will get x equals 1 over 2 root 3. Maybe we should rationalize it. So multiply by root 3, you will get root 3 over 6. So now we can say that this, I'm going to erase the x, is root 3 over 6. Okay, but let's think about that. Is there anything like a famous triangle maybe that might help? You know, you might think about 45, 45, 90 or 30, 60, 90. So we should just do a quick check and see if it is. What if I double this? What do I get? Well, if I multiply by 2, the 2 will cancel the 6, and I get that. So the ratio of this to this is 1 to 2, then that must mean if I multiply this by root 3, I get this, right? So root 3 times root 3 is 3, over 6 is 1/2. This is a 30, 60, 90. This is 30, this is 60. So the whole angle right here is 60 degrees, and that's going to be 1/6 of a circle. So you have 4 times 1/6 of pi r squared minus 4 of these triangles, and since it's equilateral, right? So this is the side length. The area formula that I choose to remember for equilateral triangles is s squared root 3 over 4. However, think about it. The s of our equilateral triangle is the same as the radius, so we can actually replace that and call it r squared. Furthermore, we know what r squared is. We just found it a minute ago. It's 1/3. Let's go ahead and factor that 1/3 out briefly. So we get 4/3 times pi over 6 minus root 3 over 4. And you might as well distribute now. So you're going to get 4 pi over 18, which is 2 pi over 9, minus the 4's cancel, and you're going to get root 3 over 3. Let's check the answers. Is it there? 2 pi over 9 minus root 3 over 3. It sure is. So don't stop because you're stuck. Just keep finding more pieces of information. Maybe that third side will trigger, and it sure as heck did. We've got the problem solved, and we're on to 17. All right, so this is the 2010 AMC 10B problem 17. It was also the 12B problem 8. Every high school in the city of Euclid sent a team of 3 students to a math contest. Each participant in the contest received a different score. Andrea's score was the median among all students. So Andrea equals the median, and hers was the highest score on her team. Andrea's teammates Beth and Carla placed 37th and 64th respectively. So 37th and 64th. So Andrea has to be less than 37 to be the highest on her team for her placement. So how many schools are in the city? Again, each school sent 3 students. You could try and make an equation, but really one way you could do it is to use the answers. But I'm just going to kind of reason it out. It has to be a multiple of 3, the total number of students, right? So if there's 66 students, right, that's a multiple of 3. Is it possible for Andrea's score to be the median? No, because for 66 students, it would be like student number 33 plus student number 34 over 2 is the median. So that wouldn't work out. So then don't try that. Try 69 students. So if there's 69 students, which student would be the middle one? The 35th place would. There would be 34 on the left of 35 because it adds to 69, and 34 on the or the right of 35, and on the left would be 34 also, allowing 35 to be the median. So Andrea could be the 35th place. What about though, is there another one that works? Let's just double check. If there's 72, that won't work. 75 is a multiple of 3. It would require, though, that the middle student be the 38th student with 37 on their left and 37 on their right. And you can't have that because that would mean that Andrea came in 38th place, which is worse than Beth's. So it can't be 75. There must be 69 students, and that's not the answer. You have to divide it by 3 to get the number of schools, which is 23. All right, this is the 2010 AMC 10B problem 18. It was also the 12B problem 16. This is actually one of my favorite problems on this contest because I learned something on it when I did it the first time. So positive integers A, B, and C are randomly and independently selected with replacement, that will be important, from the set 1 to 2010. What is the probability that ABC plus AB plus A is divisible by 3? Well, for starters, you should see that there's an A in all of these things, and even if you don't know why, you should probably factor it out. A lot of times on the test, there's things that you can do and you might question, well, should I do them? Just do them and see what happens. That's usually my advice on that. So A times this expression. Now, what is the probability this is a multiple of 3? Well, that's going to be a little bit easier because if A is a multiple of 3, then the whole thing automatically is. So then what's the chance A is a multiple of 3? Let's focus on that. Well, there's 1, 2, 3. 2010 is a multiple of 3. So there are an equal number of numbers that have a remainder of 1, remainder of 2, and remainder of 0 when divided by 3. Therefore, the chance that A is a multiple of 3, since there's the same number of those, is going to be 1 in 3. So there's a 1 in 3 chance right off the bat, automatically, depending on the value of A. But there's also a 2 in 3 chance that A is not a multiple of 3. And if A is not a multiple of 3, it would require this expression to be a multiple of 3. So it would be 2/3 times the probability that 3 divides BC plus B plus 1. So 3 divides that means if I divide this by 3, 3 will go in. Because as long as 3 goes into this, it doesn't matter if A is a multiple of 3 or not. So don't forget the 2/3 though. A lot of people forgot that, I think, and there's a wrong answer that correlates to that mistake. So how do we do this though? This is where I like the problem right here. You can learn some tactics what we're about to do from, sorry about the stutter there, from the number theory book, Intro to Number Theory. There's a way that you can write B as, you could say that B is any multiple of 3, we'll say 3 times B sub 1, plus a remainder, right? B sub naught, we'll say. So this works for any number. Any integer can be written like this, and it can be uniquely written that way. For example, 7 would be 3 times 2 plus 1, where b sub 1 is 2 and b sub 0 is 1. Now, if it's the remainder, what's it the remainder of? When you divide by 3. So b sub 0 can equal 0, 1, or 2. Then what about c? Let's do the same thing with c. We could say that it's a multiple of 3 with some remainder as well, with c sub 0 also being possible values of 0, 1, or 2. There's nothing special about 3, by the way. We can do this for any divisor. I could have said b is 4b sub 1 plus b sub 0, but in this case, b sub 0 would equal 0, 1, 2, or 3, the possible remainders when you divide b by 4. But we don't want to do this because we're not dealing with multiples of 4 in this problem, so we're not going to use that. But just keep in mind, this is a tactic you can use on other problems in the future if something similar arises. So all we're going to do is replace this with those values. So if I do that, b is 3b sub 1 plus b sub 0. And you might be asking too, why do we do this? You'll see. Okay, so then c is going to be 3c sub 1 plus c sub 0, plus b is, again, 3b sub 1 plus b sub 0, and finally plus 1. By the way, I got this solution from the official solutions from MAA. It is not my unique solution. That's how I learned how to do this problem correctly. The first time I did this problem, I actually didn't know how to go about resolving that part right there. But from the official solutions, I learned this concept. I later did Intro to Number Theory, and the rest is history. So we're going to multiply this out. 3 times 3 is 9, b1, c1, plus this times that is 3b1 c sub 0. This times this is 3c sub 1 b sub 0 plus b sub 0 times c sub 0, and then plus 3b sub 1 plus b sub 0 plus 1. Okay, now you might be thinking, that looks more complicated. How does that help us? Well, if this is a multiple of 3, right, then we can break this up into all the parts that have a multiple of 3 in them. This, this, and this. And if I group those over here, and then I add what's left. What's left is b sub 0, c sub 0, plus b sub 0 plus 1. If this part is a multiple of 3 automatically, then the only way that this is a multiple of 3 is if this is also a multiple of 3. Because if this is a multiple of 3 and this isn't, then when I combine them, it will not be a multiple of 3. So then we can just focus our attention here on this part only, but this one has nice restrictions. Instead of being 1 to 2010, it's only 0, 1, and 2. And the total choices for b sub 0 is 3 and c sub 0 is 3. That's a total of 9 different outcomes. We're going to see how many of them work now. So we say if b sub 0 equals 0. If I do that, this is 0 plus 1. 1 is not a multiple of 3, so you don't get any when b sub 0 is 0. What if b sub 0 is 1? If b sub 0 is 1, I put 1 in here, I'm going to get c sub 0 plus 1 plus 1. This is 2. I need this to be 1 in order for it to be a multiple of 3. So if b sub 0 is 1, it only works if c sub 0 is also 1. Lastly, if b sub 0 is the remainder of 2, I plug that in, I'm going to get 2c sub 0 plus 2 plus 1. This is 3 right here. This needs to be a multiple of 3 by itself, and the only one that works is 0. Obviously, if you put 1 and 2 in, it's not going to work. So 0 cancels this part out, making the rest of it 3. So this is now the value of 3. So that works when b sub 0 is 2 and c sub 0 is 0. So how many ways did we get? We got 2 ways. 2 out of 9 is this probability right here, and we're just going to clean it up now. It's 1/3 plus 2/3 times 2/9. That's 4 over 27, and this is 9 over 27. So 9 over 27 plus 4 over 27 is 13 over 27. That's E. One last quick thing to point out. I think it's interesting that this expression looks exactly like this one, except this one has subscripts on it. I think there's probably a reason for that. I don't know for sure, and I never explored it. Maybe you will, and you can leave a comment and tell us what you find out. All right, this is the 2010 AMC 10B problem 19. I'm going to solve this problem in two different ways. The first is the official MAA solution, which does not require trig, and the second solution will be my solution, which does require trig. I solved it obviously using my method, but 10th grade and below, the AMC 10 is not supposed to require trig in the past. They might change that in the future. And so you're supposed to be able to solve it without using trig, but we're going to show the trig way because it's faster. Okay, a circle with center O has an area 156 pi. You guys have asked me to draw the diagrams bigger. I'm going to try, but sorry, I have to stop talking because if I talk while I'm drawing, I might shake or mess up or something. It's harder to draw accurately the bigger the drawing. So center O, so O will be about here. Triangle ABC is equilateral and BC is a chord on the circle. So where should we put it? I usually just draw parallel to the base of your paper. So I'll call this B and C. OA is 4 root 3. Well, think about it. If you square 4 root 3, it's 48. And this is the radius squared, which is 156. Obviously, this is not that far from the center compared to the radius. So A must be down here. And we will come up to right there, and A will be located here. And I'll move O down a little bit just so we can see a little bit. So you're going to connect O to A. It says that OA is 4 root 3. So this little distance here is 4 root 3. Point O is outside the triangle. Good, we achieved that. What is the side length of the triangle? So the way that they want you to do it without using trig is this first method that we will go over. I'm going to draw it a little bit bigger so that you can see what's happening a little better, just the triangle part. We will come down here and call this O and A, and we will connect this to here and this to here. Okay, then I'm going to call the side length x, okay? So then if I make it x and I continue drawing OA through the triangle, right? So it goes to its radius point out here. I'm going to say it hits here at D. So this is B, C, and D. And it will bisect this chord because it's perpendicular to it. Okay, then this will be, I guess we'd call it x over 2, and this is x over 2. This side here is going to be x root 3 over 2, because it's a 30, 60, 90 triangle, and opposite 60 is root 3 times that. And we know that this is 4 root 3, so we can find the radius being OB, we can use that to solve this right triangle. So the radius is going to be the square root of 156. Then I can do Pythagorean on the big triangle. I'm going to get x squared over 4 plus 3x squared over 4. Oh shoot, I messed up. So we can't do that. We got the 4 root 3. So it's x root 3 over 2 plus 4 root 3 squared. And then that needs to equal 156. So let's square this out. We're going to get 3x squared over 4 is the first term, then is this times this, which is going to be 6x, because it's root 3 times root 3 is 3, times 4 is 12, divided by 2 is 6 times the x. So 6x, double that, right? What we're doing is a plus b squared, right? A squared plus 2ab plus b squared. So we're doubling the AB product to get 12x. And then the last term squared, as we said, is 48. So then from here you will add the x squared over 4 plus 3x squared over 4 to just get x squared plus 12x. If I subtract 48 from 156, I get 108. So if I do it the other way, I will get negative 108 equals 0. You got to think of two numbers that multiply to this. The first ones that come to mind for me are 9 and 12, but they don't work. So what we can do is borrow a 3 from the 9, but borrow a 2 from the 12. So for example, I'll write it, moving the 3 over gives 36 times 3, and then divide this by 2, I will now have 18 and 6. And those two numbers do have a difference of 12, so they're going to work. It is going to be x plus 18, x minus 6 equals 0. The only positive solution here is 6. So then that must be the side length. Okay, but real quick, I want to cover the second method. The second method would be if you were to connect O to B and O to C like we do here, this angle, since this is 60, right, this angle must be 150. Why? Because 150 plus 150 is 300 plus 60 is 360, and we have a full 360 degrees about point A right there. If we know that, we can call this x and this root 156, and we can use the law of cosines. The law of cosines says, and the letters are replaceable with other letters, that c squared equals a squared plus b squared. This is how I build it. It looks just like Pythagorean, but then you're going to subtract AB, which is these two numbers but not squared, right? And then cosine of whatever angle is opposite this, so we'll use capital C. So if I apply that formula to this one, the angle that we know is 150, right? We don't know this angle, we don't know that angle. So we can use cosine of 150. The side opposite 150 is this one, which we know is root 156. So we're going to square the root of 156 to get 156 equals a squared. A is going to be the 4 root 3, and this is x. So 4 root 3 when you square it is 16 times 3 is 48, plus x squared minus 2 times, and then it's these two sides again, so it's 4 root 3 times x, and then the cosine of 150. The cosine of 150 is the cosine in the second quadrant. It's equivalent to 30 degrees, but the negative version because it's in the second quadrant. So the cosine of 30, if you don't understand trig, I have a trig video that explains it, like some shortcuts and stuff. Watch that video. The cosine of 30 is root 3 over 2. So then in the second quadrant, it becomes negative root 3 over 2. Now the 2 and the 2 will cancel, and you will get 156 equals 48 plus x squared. And then the minuses cancel. Also, 4 root 3 times root 3 is going to be 12x, so it's plus 12x. And then this equation is exactly the same as what we had right here, essentially. After we move the 156 over, it looks like that as well. So that's it. That's the other way to solve it. I hope this helps. We're going to do problem 20. See you in a minute. All right, this is the 2010 AMC 10B problem 20, the last problem of this set. So two circles lie outside regular hexagon ABCDEF. The first is tangent to segment AB. The second is tangent to segment DE. Before we continue, we should probably make a picture. So I'll try and draw a regular hexagon over here. Okay, something like that. Okay, we'll label it A, B, C, D, E, F. And what do we have? Two circles. One's tangent to AB, the second. So there's one up here and one up here. Don't draw them yet. Both are tangent to lines BC and FA. So I have to extend BC out this way and AF out this way. And then this will come down here, and this will come down here like so. Okay, now where are the circles? Let's draw them in. Well, you might be thinking if it's tangent to all three sides of this triangle, then it's the in circle. We may be able to use the area is equal to the in radius times the semi-perimeter. Okay, so then what? The other circle is going to be drawn down here, and it's going to connect with the side. We're probably not going to draw it very accurately, so we're not going to worry about the bottom part. We probably don't need it. what is the ratio of the area of the second circle, that's this one, to that of the first circle? Well, you should know the similarity rules, right? The similarity rules are for all lengths, the ratios are A to B. And for all areas, the ratios are A squared to B squared. Basically, this ratio squared. So the area for us, we're looking for the area ratio of this to this. It's simply going to be r to little r squared, right? Because this is the ratio of their radii. All circles are similar to other circles. All squares are similar to other squares. So we can find the ratio of their radii and then square them. We also can use a trick here. Because no lengths are given in the problem and we're doing a ratio, we can actually make one of these whatever we want. It'd be nice if this little r was 1, so let's make it 1. Then the in radius of this circle, that's the radius coming down, it will be 1 now. And now all we're going to need is capital R squared, right? So that's what we're looking for, is the big radius, and then we're going to square it. So now how do we go about that? Okay, so we have the area equals the in radius times the semi-perimeter. What else can we use? We can also use the area of an equilateral triangle. This is the area of any triangle equals its in radius times its semi-perimeter. But an equilateral triangle is equal to its side length. I'm going to say it's x squared root 3 over 4. Usually I use s, but we're already using s for semi-perimeter. So then I can set these equal, and I know the in radius is r, so what would the semi-perimeter be? If the side lengths are all x, then the semi-perimeter would be 3x over 2. So we can say 3x over 2, the radius is 1, so this just goes away. The area is the semi-perimeter, right? So if the in radius is 1, then 3x over 2 is the semi-perimeter. That has to equal this, x squared root 3 over 4. Now, we can multiply by 4 on both sides. You will get 6x equals x squared root 3. You can actually divide by x because we know it's not negative, so the squared goes away and the x goes away. Divide by root 3 to get that x, the side length of the equilateral triangle, is going to be 2 root 3. Okay, so 2 root 3 is this. Then if it's 2 root 3, then half of it, which is this part, will be root 3, right? And that 2 root 3 is the side of the hexagon as well. That means this is 2 root 3 and this is 2 root 3. Okay, so we're good so far. How are we going to get the big radius though? Let's come down with this straight through that point, right through here, and come to the center of this, and we will draw over to the point of tangency. It's going to make 90 degrees, right? And so any center drawn to a point of tangency will intersect that point at 90 degrees, the other line, the tangent line. Okay, so then what can we do? We could have similar triangles here. We've got one, and this is the big radius r. So if we just knew like the hypotenuse, it would be good. This part here isn't too bad because it's a 30, 60, 90 in which this is root 3. And so this is the 30, then opposite 60 is going to be root 3 times this. So this is 3. That means the height from here to here is 3. All right, what about this piece though? We kind of need that also. Let's draw it again right here. And that's because I'm going to draw that a little bigger, that part, so you guys can see a little bit. If this is point F, this is 120. And this is 2 root 3 and 2 root 3. You can drop the altitude right here. It's a isosceles triangle. It will bisect the base. It's perpendicular. In addition, because the whole angle was 120, this will be 60 and 60. And this is 30. So if opposite 90 is 2 root 3, then opposite 30 is half that, root 3, and opposite 60 will again be 3. I probably could have just been smart and realized that from here to here is the same equilateral triangle as there, so this distance must be 3. It feels dumb now to have done all that work, but oh well. So 3 and 3, this distance here going from here down is 6. And this is also r. So we can now make a ratio of similar triangles. It's going to be the radius to 1, r, that is equal to the big hypotenuse to the small hypotenuse, because this is also 90. So the big hypotenuse is r plus 6 plus 3. It's r plus 9. And then the small hypotenuse is just this one right, no, not that whole thing. It's just this part here to here. And since this radius is 1 and the whole thing is 3, that part must be 2. And we can put it over 2. Cross multiply, you will get 2r equals, r plus 9. And then when you subtract r, you get r equals 9. Again, all we want is r squared, so that means r squared is 81, and it is the answer. See you in the next set.